All right. So in the last lecture, we looked at this problem, which was weighted interval scheduling, and then we looked at the algorithm for it, right? And we saw how using dynamic programming we could get a polynomial time algorithm for this problem, where we actually had to find an ordering and finding an ordering, or you know, or finding a subset. There are 2 to the n many subsets, and we could actually do this in polynomial time. There was a question. I hope that was answered. Ayush, you had asked. Is Ayush here? Okay, he's not here. All right. So I hope that was clear. How to compute PJ, what I said in the email, and like in the note. I also copied that in the note here, Teams. So now today, what we'll try to do, we'll try to get a more general framework of dynamic programming using the same, sort of principles that we used for designing the algorithm for weighted interval scheduling, and we'll see how to do that. Okay. All right. So first thing that is going to be okay. So let's say the topic is going to be principles of. So the first thing is that if we look at the solution or whatever, once we have this array M, then basically we have the solution, right? And this array M is built whenever, if you look at the recursion, then it is built for, that is the other algorithm, compute opt. So here this array M basically has the solution, and you return this value Mj, and it always depends on the lesser value. So the first thing that can be is, so let's first look at the examples, example of weighted interval scheduling. So array M has, all the information about the solution. And Mj depends on entries Mi, let's say, such that I is less than j, right? So why do we have to then, do it recursively? Why can't we just start with M0 is equal to 0? This we had defined anyway, right? And then just fill M in, increasing, or, in the other direction. Instead of starting from Mn and then, coming down, then we fill it from the other direction. And that is again going to be then the algorithm becomes very easy. And what is that? Let's call it iterative compute opt. So instead of the recursion, we are going to do the iterative version now. And what will it do? It will just put M0 is equal to 0. And for j is equal to 1 to n, Mj is equal to whatever the formula we had. Max of Vj plus Mpj, right? Comma M j minus 1, right? And this is it. And for. And finally, you can return whatever M. Right? So So this way we don't have to actually go through the recursion and then argue about the running time, that okay, put the measure and so on, because now running time is very easy. How much time does it take? Suppose you have computed the PIs. Suppose PIs are computed. This was PIs. And arrays sorted or intervals are sorted in by finish time. Then how much time does it take? Then how much time does this algorithm take? Somebody will have to speak up.
It takes constant time in every for loop.
Exactly. So for
As
every
in,
j, write it here. Somebody's saying something here. What are you saying? Yeah, order and time. Angan, you can unmute yourself and tell also. That might be faster for me to communicate. Okay, good. So for every whatever value of j, this operation is being done, and this is constant time, right? So total time is order n, right? Which is what the running time we had of the earlier algorithm also. And now we have filled this mj. Now using this mj, m whatever this m array, and the find solution algorithm. What is it called? Find solution. Yeah. This find solution algorithm. We can actually find the solution, right? Good. So this is just to illustrate that, okay, I mean, you can go for iterative methods rather than the recursive method. And this is what we'll be using now whenever we'll do dynamic programming. We'll be going through this side from the smaller sub problems, and we'll keep building the larger sub problems. So this kind of gives us now the general framework of dynamic programming, and it is going to have three main elements, right? So what is the outline? The first, the sub problems should not be too many, right? Here we had just n sub problems and so on. So there are only a polynomial number of sub problems. Second is that given the solution to the problems, the solution of the solution to the subproblem, the solution of the problem should be computed easily, right? Computable easily. So solution to problems, solution to subproblems should give, let's say, just draw an arrow, should give easily solution to original problem. And this sometimes happens because, the original problem is one of the subproblems itself. So then it's fine. Like here, the subproblems that we were solving, if we just go to MN, then that turns out to be the solution to the original problem, right? Might be a subproblem. And then we are good. And then what do we want? That there is some ordering in subproblems. and solution to larger subproblem can be obtained using smaller subproblems using a recurrence. Right? So, like these two are the crucial steps, of course, that how to get to the subproblems. So there are two things, like subproblems and recurrences. So sometimes defining the subproblem is easy, that okay, you just there is an ordering and then you just remove one element or something and that gives you a subproblem. But how to relate those subproblems in terms of recurrences is not easy. Sometimes you can write the recurrences more easily and that gives you what subproblems to solve, like we saw in the weighted interval scheduling case. That we look at the problem structure and from there we get the recurrence, and then from there we get what subproblems we need to solve. So this, like, which one to go for first is not very, like, there is no rule for that. But that comes from, like, if you solve more and more problems and then you get used to the thing, and that's how it happens. Okay. So let's now look at, so this is the basic framework, and now look at another problem that we'll be solving using, like, this framework of dynamic programming. Okay. So it's called segmented least squares. Okay. So the idea is actually simple, that okay, you are given some endpoints in the plane x1 x1 y1 x2 y2 xn yn, right? And let's say that they are ordered somehow, that x-axis, okay, and they are not the same. Okay. And now you want to give a line, right? So find a line let's say L is equal to ax plus b, that minimizes the, like, somehow that is best fit to the points. And how do we define this best fit? Is that it, minimizes some error. And how is the error defined at? Squared distances, sort of. So error of L comma P is equal to summation I is equal to 1 to n. Now you just look at what should the yi would have been because of the line. So yi minus axi minus b. So it should be axi plus b, right? Because the line is ax plus b. So the yi should have been axi plus b. And you divide that from yi, and then you take the square and sum that for all the points. Right? So this is the error which you want to minimize. Okay. Good. So the thing is that if you just want to find one line like that, then actually there is a closed form which gives you this line given endpoints, which is just a is equal to, I'm just going to copy it down, n summation I xi yi minus summation I xi summation I yi, right, divided by n summation I xi square minus summation I xi whole square, and so on. So this is A, and then this is B is equal to summation I yi minus A summation I xi divided by n. Okay. So anyway, so there is a closed form for finding this particular line that minimizes this particular distance, right? So problem solved. I mean, we don't need to do anything, right? But the problem is that in the real world data that we get, it's not that we always want to find one line. Like, of course, if we get some data like, like this, then it seems like, okay, we want to find some line, through these points, whatever, right? But what if we get some data which looks like this? More points maybe, right? Then it feels like that, okay, if we want one line, then that line would be like, whatever, not like this, but like this. But then this line does not seem to do justice to the data, right? Maybe we should have, two lines. One goes like this and one goes like this, right? So sometimes two or more lines might be needed. To minimize the error, kind of, right? Okay, good. So now how do we formulate the problem? So what if we hardwire things? Like, so what if we want that, okay, get two lines or, any X number of lines, right? Then what is the problem with that? It's not flexible enough. If we hardwire that into the problem definition, the algorithm or the solution will always going to look for some X number of lines, right? So not flexible enough. Like we hardwired two and now we get a data which is like whatever, like this, and then like this, right? So this takes basically three lines. Okay, good. And what if we don't do that? If we just say that, okay, find any number of lines such that the total error is minimized. So this is the other way, right? Once you fix it, the other way is now you're not fixing it. You are like, okay, I don't care. Find any number of things such that the total error is minimized. So what is the problem with this?
We get n lines.
Yeah, you can get n lines, right? Or even n minus one for every consecutive pairs. Like, yeah. So or n over two, whatever. So you can get n lines, right? And then error will be zero, right? So then what can be a trade-off? Anybody can suggest that? Or how can we get something in between these two?
Can redefine the error function to like penalize for the number of lines as well.
Exactly. So as Shravan says that look at the error function and have some penalty for number of lines. Okay, so we don't look at the error function, we'll just put a penalty for every additional line that you add, right? So that is one way to deal with it. So what do we do? So let's now write the formal problem definition. Okay. So suppose we are given some set of points p is equal to this set x1 y1 to xn yn, right? And x1 is less than x2 is less than xn, right? And let's say pi is point xi yi. Pi denotes this. And now we want to partition P into segments. And what is a segment? segment is a subset of P of the form, Pi to Pj. P of the form Pi plus Pj, right? And yeah, that's it. So for each segment S, in the partition, now we go for the, what is the penalty? The penalty of this segment is going to be sum of two things. To be so what is, or okay, actually, let's just say for each segment S in the partition, let's not do it that way. Let's just say that for a partition, the cost of the partition, let's say, for a partition, the cost of that partition, for a partition, let's say P, which is equal to some S1, S2 to Sk, let's say K we have not used, right? Hopefully, okay. The cost of that partition, and this partition is into subsets. So let's say cost of this partition is equal to C times the size of P, right? Plus S, let's say just I in K. Again, penalty of, should I use penalty or what should I use? And whatever error of SK, SI, right? And what is this error of SI? This is, now you just go through this formula and find this. Where is this formula? Error of L comma P. So you find the closed form for that particular segment, and you see what is the minimum error for that. So you find the line using this formula. You get the closed form, and then you find the error for that. So find the closed form. And find the error for that. So any questions till now about the problem formulation? What did we do? We looked at the set of points, and now we are saying that, okay, what is the final aim? Final aim is that we want to divide this into parts. So let's say if this was the data set, then we would like to divide this into this part, and then we find the line that, the best line that passes through this part, the best line that passes through this part. And then since we are now using two lines, so we'll put some penalty 2 times C plus E1 plus E2. Right? So let's say the error of this was E1, this was the error of this was E2. Right? If this was the case, then we'll if we are partitioning in 3 parts, then we'll get 3C plus E1 plus E2 plus E3. Right? And now this sort of captures what we wanted to do, because if we get too many partitions, too many parts in the partition, or yeah, too many segments, let's call it, then the first part, this will be more, right? So this captures the trade-off, right? And we can tweak C to, penalize more or less. for more segments. Good. Pull this down. Not yet at the algorithm. Okay. So any questions till now?
Sir, in a segment, do they necessarily need to contain consecutive points?
Yes. So that is why I said that this is pi plus j and so on. So segment is continuous points. Subset of p of the form this. So this is like continuous points. I mean, you don't want to be like, that some random point is here, which is coming after that, and you want to just map that to this line. I mean, again, that's just a, problem definition. You can define it that way, but here we mean consecutive. Any other question? Okay, if not, then now let's see how we will go about designing an algorithm for this problem. Start here itself. Not here. Okay, so again, like we in case of weighted interval scheduling, what did we have? We had that we looked at the last interval and what were the subproblems that we get, or what were the things where mm, with which this could combine to get a solution, right? But there is now some problem that, I mean, that was a subset problem that we wanted to find something, and then we wanted to combine this interval if this is in the solution or if this is not in the solution, and that is why we were thinking. Now we have a slightly different kind of problem. This is a partitioning problem. So it's not that either this guy will be in the solution or this guy will not be in the solution, the last guy, but now it has to be in a solution somehow. But the question is which partition it will be in, right? So slightly different way of thinking is needed, but still let's look at the last point. Pn, right? So we know one thing we can say for sure, that is that, okay, whatever interval, this is part of, whatever segment this is part of, right? So if we can identify this last segment, that Pn is part of, let's say some Pi to, or let's say Pi plus 1 to Pn. Suppose this is the last segment of the solution. Then we know that the solution will be like opt of. Okay, so let's also denote opt of I. So opt for optimum solution for P1 to Pi. Okay, I'm doing this. If I'm going to ever print this, this will be problematic. Can we do something like this? Just shrink it a bit and okay. All right. So now what will it be? Opt of I plus C plus So again, this is the value of the optimum solution. I've written opt of I, but this is like, okay, value of, this is not optimum solution. I mean, yeah, for the error of the optimum solution, this quantity basically, cost. So let's call it cost of I itself because we want to be consistent. Okay. All right. So cost of I is equal to, the cost of n is equal to cost of I in that case plus C plus error of, let's say, so error, now we have like two parameters, I comma n, right? I plus 1 comma n. Or let's say I comma n if you want to say, then let's write it here, I minus 1 just to be consistent. So what does this mean? So again, like this C is cost, okay. I hope you can understand that this C and this C are different. This is capital C, this is the penalty, and this is the cost. Okay, so, or yeah, I mean, or maybe I should use just the opt. Yeah, anyway, cost is the cost, so I should use opt. I'm using this. Okay, and so what does this say? This says that, okay, you have any data, whatever you have, right? Look at this guy, this last guy, this Pn. And suppose you know that, okay, this is the interval from I plus 1 to n that contains this point Pn. So this is going to be one segment. Now you find the optimum solution of the previous segments, whatever that is. So you find the opt of that, plus you add one penalty for this segment, plus C, and then whatever the error is of this guy. And that error just depends on the points there. Because from the points, you can get the optimum line that passes through those points. And for that line, you can find the error. So this error is, there. Error of I plus 1 comma, I comma n. Okay, we did I now. So suppose the interval starts at I, and this is I minus 1th point, and then so on. Okay, good. So is this clear that, how the optimum solution will be? If we know the final interval, right? Which interval is going to be there? Is that clear?
Yes, sir.
Okay, good. So now, okay, superimpose these things. I should put this down and this putting the other one down. Yeah, good. Okay. All right. So now we are quite close. So this is the reasoning that we do for the nth one, but the similar reasoning now we can do for computing any opt of j. So we want to compute now this opt of j for all the smaller ones, right? Because we want this opt I minus 1. So we want to compute opt j now for all j in whatever 1 to n sum. And these are the subproblems, and this n will opt n will give us the answer. And the same logic now we apply for this opt j for any j. That, okay, now we don't know what is the interval going to be, where the interval will start. So we have, like, again, like, whatever we have, and this is the point j. This is some arbitrary point j. Then we have more points, whatever. But for this arbitrary point j, again, it will be part of an interval that starts from I, some I, right? And then the error for this, and then this is going to be the other subproblem for which we would have already computed the opt, right? So what do we get? That the recurrence sort of. So for the sub problems, on let's say P1 to Pj, that is what we want to solve, right? So opt of j is equal to minimum over all 1 less than I less than equal to j. Again, we had this term error ij, right? So we can just write error of I comma j plus c plus opt of I minus 1. Again, the same thing, that this is I minus 1, and then we have this opt of I minus 1. The best way to solve this, plus c for another segment, and error of I comma j to accommodate the error for this, right? So this is the recurrence that we get, right? And then also, I mean, from this we can find the solution also, that the segment, I mean, this just gives you the optimum value, but we might want to find out the optimum solution also, that what are the segments, right? So the segment pi plus 1 dot 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 pj, right, is used in the solution. Or optimum subproblem solution, right? Optimum solution for the subproblem for pj, right? If and only if the minimum is obtained using the index I. So this I should be the one that minimizes this quantity basically. So this quantity is minimized for some I. So the minimum should be obtained using that I. If the minimum is obtained using that I. Right? So this gives us the recurrence. This is our recurrence basically. Right? And then now, like, we are more or less done. Now we have got this recurrence, and now we just need to compute this error of I comma j. So first thing, we need to find the error I comma j for all I less than or equal to j. For all j. Right? And then if we have that, then we can just solve the opt problem, right? So any questions about this? Till now, whatever we have done, please ask if you have any question. Because now, like, we are almost done with the algorithm. I'll just describe the algorithm now. Okay, good. If not, then let's look at the algorithm. And the algorithm is very simple, as I said. So this is the array M that will store the solution. So store the solutions to the subproblems, right? M0 is equal to 0. You start from there. And for all pairs, yeah, I mean, of course, you should start with, there should be one basic, the base case should be there, that when you don't have any points, then there is no penalty, nothing. So you'll need that, because, of course, then finally for opt1, you need to solve this recurrence and so on. So you start with M0 is equal to 0. And for all pairs, as I said, that you need to compute the error for every ij. So for all pairs, compute the least square error Eij for the segment Pi to Pj. And once you have that, once you have the error part here, now you can just solve the recurrence iteratively. That you already store the value of the smaller i's in M, and then you build up to the larger i's, right? So first you compute this. So we'll see, first let's go through what the algorithm does. And then for j is equal to 1 to n, use the recurrence, whatever, let's call it, this recurrence 6.7. If they are calling it, it's there in the book, and the number is 6.7. So use the recurrence to compute mj. So opt j here we are calling it, you can call it mj. So use this recurrence to compute mj, and how you just, for every smaller one you have already computed, you start from 1. So induction is going to be on this. The proof is going to be by induction, that for every smaller one you have already computed, and for mj you will only need the smaller ones to compute mj, and now you can compute it, right? And then you finally return m. Okay. So the correctness can very easily be by, like, again, like, is by induction. By induction, you'll say that all subproblems which are smaller are computed correctly. So let's say we are doing it for now like mj, right? So all the smaller subproblems are computed correctly by induction and induction hypothesis, and so mj is is computed correctly due to the recursion, due to the recurrence. 6.7, right? Because 6.7 says exactly that what is opt of j? Opt of j is minimum over all I less than j, error of ij plus c plus opt of I minus 1. Right? So this is the correctness. And a quick runtime analysis if we want to do, let's say. Okay, so let's call it 1. And let's call this 2. So how much time does 1 take? So 1 has n square pairs, right? For I and j, we have these order n square pairs and choose 2 pairs. So we have order n square pairs, and for each of them, we have to compute the least square error for the segment that, right? So now we have these least square error ka formula. This one error, and before that we need to find out this a, which uses these endpoints and so on. So basically, you have these endpoints, and you need to find things out. So if you figure it out, you'll see that this can be done in for each pair in order n time you can get it. So total time for step 1 is order n cubed, right? And for step 2, what are we doing? For j is equal to 1 to n, use the recurrence to compute mj. And what is the recurrence doing? Recurrence is going for all I less than or equal to j, right? And then for each such I, it is taking constant time to compute this, because error is already computed now for every pair. Opt I minus 1 is already computed. So you just go and look that up in the array, like whatever this M array. So that is already computed. This is already computed. So for every I, this is already computed. So for every J, how much time it will take? Order n time, because J can be linear, right? So total time, order n square. So now total time for algorithm, order n cube. So we did the correctness analysis, we did the running time analysis, but there's one thing we have not done, that is the finding the segments, right? And that again, since we had this whatever this recurrence and the result for it, so finding the solution, use the criteria in recurrence. And what is that? Again, let's just, do it for the sake of completeness. So we do the find segments. Now we already have this, use the, whatever array mj, right? For doing this, because now we know that for whichever I this value becomes minimum, optimum solution for the sub problem for pj, if the minimum is obtained using that I, right? So now we have this array. So if j is equal to 0, then output nothing. Else, find an I that minimizes this value. And if the I minimizes this value, then what did we have? That pi to pj is the result. Output the segment this and the result of find segment I minus 1. Right? So this is for find segment j. Right? So these are again subproblems. Finally, what do we want? Find segments n. Right? So this is now a recursive algorithm, right? That we call find segments n. Then it goes and looks for an I that minimizes ei plus, so you already have this eij, right? Plus c of mi minus 1. And then you call it recursively on that find segment I minus 1. So how many recursive calls are made? Maximum. And in each recursive call, how much time is it taking? So suppose again you have this eijs. Eij and m are computed. Then how much time will this take? So how many recursive calls? And how much time in each recursive call? Okay, anyone? How many recursive calls this, find segment thing can make? Total. For n, it can make for something n minus 1 only at max. So it is always making a recursive call for a smaller set or smaller j. So how many total recursive calls can be made for find segment n? Please speak up. I'll start taking names like randomly. Please, somebody. This is not that hard, I think. Or I have been like very terrible in explaining or something. So now we have found the solution. We have found the value of opt, and now we want to find the segments, that which are the actual segments. And for that, we start with the n, and we want to use the same information that we had for opt j, that, okay, whichever value minimizes that. So we had this, right, that we have this set of points. We start with n, and then we want to find that, okay, which value of I minimizes this quantity. We have stored that for every I, right? Now we have the opt also for every I. So we have the opt of every I minus 1. And now we want to find the error, and we want to sum these quantities, and we want to see that, okay, what minimizes this. So, and then we look at that I, make this a segment, and output that union the best solution for the previous thing. And what is the best solution for the previous thing? We call the same function, the find solution on this last guy. Right? So how many calls will this procedure make at maximum? order, you have to tell in order only. I don't want the exact number.
Order I.
Order j or whatever. Yeah, the order n basically, because we start from n, right? So order n, basically at most n recursive calls. Actually less than or equal to n recursive calls, which is order n. And how much time in each call will it take? So each call is doing what? Each call is finding an I that minimizes this. So it goes through all the I which are less and and for each of those I's, it calculates, this quantity, Eij plus C of Mi minus 1. And this quantity is there already, right? Because Eij is stored, Mi minus 1 is stored. So it has to find that I that minimizes. So how much time in each recursive call? Again?
Order I.
Order I. Okay, or order n, because we want to find an I. So, I mean, order n because n is the upper bound, and for every time this j is called, this j is at most n. So we have order n time for this. So total time is order n square, right? For this, for finding the solution once you have Eij and m. But we saw that Eij itself takes order n cube time. So basically the total running time is order. Good. Any questions?
Excuse me, sir.
Yeah.
So why can't we calculate EIJ for all, like in order n square time only?
So depends on how much time you take for one Eij.
So like if we like store some, like if we pre-compute some stuff, we can do it in order one as well.
That is going to be, you are right, it can be done, but that I want you guys to figure out by yourself. Okay?
Okay, sir.
Yeah. So you are right, it can be done, but I'm going to give that as an assignment. Okay? Any other question? Okay, so good that you pointed that out, and that is actually true. That if we are clever, then we can Eij for all Ij can be computed in order n square time, and you can start thinking about it, because now itself I'm telling that this is going to be an assignment question. Good. So any other question apart from that? Okay. If not, then thank you for coming, and we'll meet again on Thursday. Thank you.